Hi all. In this video we're going to look at section 3.1 on systems of linear equations in two variables. To start off with, we'll look at the definition of a system of linear equations, which is a grouping of two or more linear equations, each of which contains one or more variables. So we see an example A and B. In each case we have two equations, and the first one, our variables are x and y. In B, we've got first equation, second equation, with the variables a and b in each of those. In this section and for our class, we're going to deal typically, and in fact almost exclusively, with systems involving two equations with two unknowns. Very important is this next line. We need to remember a solution is a value of the variables that makes each equation a true statement. That is, every equation needs to be a true statement for it to be a solution. So let's look at example 1 here. Looking at example 1, we're asked to determine whether the given ordered pairs are solution of the system of equations below. So we need to determine whether these points in A and the point in B make both of the equations here in the system true. So remember, this ordered pair represents an x and y value. So let's evaluate that first equation. So plugging in the x and the y, the -2 for x and the 3 for y, we're going to determine whether or not this statement is true or false. That's our goal. So working through the left-hand side here, 2 times the -2 is a -4, plus 3. We're trying to determine whether or not that equals 2. Continuing to work on the left-hand side, a -4 plus 3 is a -1. -1 equals 2, I'm pretty sure that is a false statement. So this is not a solution here in A. Again, this has to make both equations true. So let's look at what we're going to do on part B. We're going to plug out 3/2 and -1 into the first equation. That'll be 2 times 3/2 plus a -1. Again, we're going to determine whether or not that makes this first equation true. Working through the left-hand side, 2 times 3/2 is 3 minus 1. 3 minus 1 is 2, which does indeed equal 2. That's a true statement. Looking back up at that second equation real quick, that second equation is 4x minus 3y equals 9. Plugging in 3/2 for x and -1 for y as we work to determine whether or not this is a true statement. 4 times 3/2, that's the same as 2 times 3, that's 6. Well, -3 times -1 is a +3 equals 9. Let's see, 9. I'm pretty sure that equals 9. This is also true. Since this ordered pair, this point made both equations true, it's indeed a solution of the system. So it's a solution of the system of equations. And that's what we mean by a solution of the system. Next, we want to talk about visualizing what the solutions of a system of linear equations looks like. With two equations and two variables, 3 options are possible. And most of the time, it's going to look like this first one. If I just randomly pick values, if I graph one line, I graph another, the 2 lines will intersect. In this particular example, the slopes of one was positive and one was negative, and that's what this kind of graph will basically look like. But I can actually have 2 positive sloped graphs intersect, and similarly I can have 2 negatively sloped graphs intersect. But intersecting lines is a very common occurrence, and that will look like the solution we did. We're going to plug out 3/2 and -1 into the first equation. That'll be 2 times 3/2 plus a -1. Again, we're going to determine whether or not that makes this first equation true. Working through the left-hand side, 2 times 3/2 is 3 minus 1. 3 minus 1 is 2, which does indeed equal 2. That's a true statement. Looking back up at that second equation real quick, that second equation is 4x minus 3y equals 9. Plugging in 3/2 for x and -1 for y, and the y, the -2 for x and the 3 for y, we're going to determine whether or not this statement is true or false. That's our goal. So working through the left-hand side here, 2 times a negative 2 is a negative 4, plus 3. We're trying to determine whether or not that equals 2. Continuing to work on the left-hand side, a negative 4 plus 3 is a negative 1. Negative 1 equals 2. I'm pretty sure that is a false statement. So this is not a solution here in A. Again, this has to make both equations true. So let's look at what we're going to do on part B. We're going to plug out 3 halves and negative 1 into the first equation. That'll be 2 times 3 halves plus a negative 1. Again, we're going to determine whether or not that makes this first equation true. Working through the left-hand side, 2 times 3 halves is 3 minus 1. 3 minus 1 is 2, which does indeed equal 2. That's a true statement. Looking back up at that second equation real quick, that second equation is 4x minus 3y equals 9. Plugging in 3 halves for x and negative 1 for y as we work to determine whether or not this is a true statement. 4 times 3 halves, that's the same as 2 times 3, that's 6. Well, negative 3 times negative 1 is a positive 3 equals 9. Let's see, 9. I'm pretty sure that equals 9. This is also true. Since this ordered pair, this point made both equations true, it's indeed a solution of the system. So it's a solution of the system of equations. And that's what we mean by a solution of the system. Next, we want to talk about visualizing what the solutions of a system of linear equations looks like. With 2 equations and 2 variables, 3 options are possible. And most of the time, it's going to look like this first one. If I just randomly pick values, if I graph one line, I graph another, the 2 lines will intersect. In this particular example, the slopes of one was positive and one was negative, and that's what this kind of graph will basically look like. But I can actually have 2 positive sloped graphs intersect, and similarly I can have 2 negatively sloped graphs intersect. But intersecting lines is a very common occurrence, and that will look like the solution we just looked at a second ago, where we will have one ordered pair that represents this point of intersection right here be our solution. Other things that can happen, we can have 2 parallel lines. If the 2 lines are parallel, you'll notice they have no point of intersection, and the solution will be, well, there's no real solution. Alternatively, we can have a graph that looks like this. One line was already graphed, and there's in red another line, and here in green is the second line. Oh wait. Those are exactly the same line. If they're exactly the same line, then any point that falls on that line is a solution of the system of linear equations. And you'll notice there's an infinite number of those, but they are those values where they intersect. Next, we're going to talk about methods for finding solutions. And there's 3 that we'll discuss in this book. The first one is graphing. Graphing gives us a good idea of what it is we're looking for and the meaning for that. We won't do a whole lot of examples that actually entail graphing, as this is not as accurate as the other methods. The other 2 methods are substitution and elimination, and we'll look at how those work as we get there. In example 2 here, we're asked to solve the following system by graphing. So taking my first equation, I've got x plus y equals 1. I'm going to make a little t-table here. And I'm going to find the x and y intercepts if I can. Plugging in 0 for x if you want to think about covering up the x. I'm left with y equals 1. Well, that wasn't too bad. Covering up the y, kind of visualize doing that here. You should see that x equals 1. So for that first line, I'm going to point at 0, 1, and a point at 1, 0. Drawing the line between those 2 points. Let's line this up. Got a point here. Got a point down here. I'm using my handy dandy little ruler here. I got a line that looks kind of like that. Alright. Looking at our next set of next equation, negative 2x plus y equals 7. Same idea here. I'm going to find the x and the y intercept, plugging 0 for x and 0 for y respectively. Plugging in 0 for x, you can kind of think of covering up that negative 2x, so we'll get that y is 7. Covering up the y, we're left with the equation negative 2x equals 7, or x equals negative 7 halves after dividing both sides by the negative 2. So we'll point here at negative 7 halves. Let's do that line in green. I'll point at negative 3 halves 0 and 0, 7 here. And then drawing the line connection, which is kind of like that. And I should see here that I have a point at about negative 2, 3. Checking to see if that point at negative 2, 3 is a solution. Well, let's go through that. Plugging that into the first equation, I'll get a negative 2 plus 3 equals 1. Well, negative 2 plus 3, that's 1 equals 1. That works. Checking into the second equation, negative 2 times negative 2 plus 3 equals 7. I'll get negative 2 times negative 2 is 4. Plus 3 is 7. 7 equals 7. Looks good. So the point at negative 2, 3 is indeed a solution. You might note with graphing, you have to be extremely careful to be able to see that point exactly lined up. And I tend not to be able to do that particularly well. Graphing, in theory, will work just fine. That should be a point that you would find on the graph of these two lines. But the other two methods we'll use will always work. In example 3, we're asked to solve a system of linear equations using substitution. Now, substitution, kind of like the name implies, involves taking one value of the variable and plugging it into the other equation. So what we're going to do here is we're going to first pick one of these two equations, and in general it doesn't actually matter which one, but pick one of the equations, solve it for one of the variables. You may notice that in the first equation the x is by itself. So let's actually pick that as the variable we're going to solve for. We're going to take that x plus 2y equals a negative 6 and solve the equation for x, that is, get the x by itself. In doing that in this particular problem, we're going to subtract the two y's from both sides. We should end up with x equals a negative 6 minus 2y, or negative 2y minus 6, it doesn't matter which way you write it. But we now have the x by itself. Very importantly, we need to take this amount and plug it into the other equation. Doing that will give us 2 times x. Well, x is this amount right here. So we're going to put that negative 6 minus 2y there in for x. So 2 times that minus 3y should equal 16. And we're going to solve that now for y. Very nicely, when we write the equation this way, I only have one variable. I only have the variable y involved. And that's what substitution does for us, is it cuts down the number of variables involved, which gives us something we can actually solve now. Distributing the 2, we get a negative 12 minus 4y from this first part right here, minus 3y should equal 16. Just bringing down the rest. Combining like terms on the left-hand side, I'll get a negative 12 minus 7y equals 16. Adding 12 to both sides, I'll have a negative 7y equals 28. So finishing this off, I need to divide both sides by a negative 7, and I'll get y should equal 20 divided by negative 7 should be negative 4. So I know the value of y. Now this is my y. A solution of the system is the point. It's the x and the y values together that make this up. So I need to find the x value. Well, if negative 4 is the y value, I know x is negative 6 minus 2 times y. I'll plug that negative 4 in for y into that equation and get that x should be negative 6, that should be plus 8. And multiply negative 2 times negative 4. So I'll have a negative 6 plus 8, or x equals 2. So my solution of this system should be x equals 2, y equals negative 4. And you really want to check this back in the original. Let's do that. So plugging this into the first equation, we'll have 2 plus 2 times a negative 4 equals negative 6, or 2 minus 8 equals a negative 6. Negative 6 equals negative 6. That indeed checks. That was the first part of my check. Second part of my check in the second equation, 2 times 2 minus 3 times a negative 4 equals 16 is what we're trying to determine whether or not that is true. 2 times 2 is 4 plus 12. Let's see if that equals 16. Looks like it does. This does indeed check. So my solution here should be 2, negative 4. Example 4 asks us to solve a system of linear equations using elimination. With elimination, there's a few different possible steps we can use in setting these up. One thing we can always do is to multiply the entire equation by a non-zero amount. That's nothing new with solving equations. What is kind of new with this in a system is we can add the two equations together. So I want to find some variable that will allow me to add these two equations together and be able to cancel out a variable. That's really my goal. So let's kind of look at this. I have 4x minus 5y equals 16. That's one of my equations. And I want to try to figure out if there is some way to get rid of either the x or the y variable by multiplying by some number and then adding the two equations. For most of you, this is actually easier than it sounds. So let's go through this. What I want to do is I want to multiply the second equation by negative 2. I multiply everything in the second equation by negative 2. If I do that, distributing negative 2, I'll get a negative 4x minus 6y equals plus 6. Now, what you'll hopefully notice is that if I add these two equations, negative 4x, then the 4x minus 4x, the x terms are going to cancel out. And I'll be left with, well, negative 5y minus 6y is a negative 11y equals 22. Again, here I was adding the two equations together and seeing if this was my overall result. Well, that's a lot easier to solve. All I've got is one variable. And this will tend to be a fairly simple thing to do at this point. Dividing both sides by negative 11 to get rid of the negative 11. I've got y equals negative 2. Once I have the y value, I can choose either of the first two equations. It doesn't matter. Plug the negative 2 in for y, and then use that to solve for x, because I only have one value, one variable left. So I should have here 4x plus 10 equals 16. Subtracting the 10 from both sides, I'll get 4x equals 6. Dividing both sides by 4, I'll get x equals 6/4, or simplifying 3/2. So I expect my solution to be, just running over here where I have some room, is 3/2 negative 2. Now, as we did before, you really want to check this. I'm going to do it up here on the right. We got this 3/2 from the first equation, so let's actually try checking in this second equation. So 2 times 3/2 plus 3 times negative 2. We're trying to determine whether or not that equals negative 3. Multiplying this out, we'll get 3 plus, well, minus 6. Let's see if that equals negative 3. 3 plus negative 6 is negative 3 equals negative 3. And that did indeed check. We could also check in the first equation. Should have worked there. But we're going to see our solution using elimination was 3/2 negative 2. And in fact, our solution using any method should have been 3/2 negative 2. Let's go back through this. With elimination, first you want to multiply one of the equations by some non-zero constant, so that when you add the two amounts together, one of the variables cancels out. Once we've done that, solve for that remaining variable, take that amount, plug it back into either of the first two equations, and find the other value of the other variable. And that's how elimination works. So those are our three methods: graphing, substitution, or elimination. And typically, you'll be able to do whichever method you want, though substitution and elimination are the two that you should focus on. Hope this helps.